Okay, in the first two videos we learned how to use the Vesper theory table. Today we need to talk a little bit more in detail about bond angles, which is kind of a nuanced topic, but it does come up often enough you guys should have at least heard of it. So these bond angles on the periodic table are kind of idealized, it even says ideal bond angles, where we don't distinguish between single bonds, double bonds, triple bonds, and lone pairs. We assume all the groups are essentially the same with regards to angles. What we need to look at is it turns out that not all, so the foundation of Vesper theory is that electron groups repel each other and lead to a geometry. Not all groups repel equivalently. So basically the idea is lone pair, so this is the amount of repulsion. Lone pairs repel more than triple bonds, which repel more than double bonds, which repel more than single bonds. So the idea is that electrons repel each other, they try to get as far apart as possible, and that's what leads to these geometries, but it turns out not everything repels equally. The logic on this, for at least these three, single bonds only have 2 electrons, this is 4, this is 6, more electrons means more repulsion. This one only has 2 also, but typically when we look at molecules, what we see is, we have, say we have 2 carbons. We have protons here and protons here to help hold these electrons in check. If you had, something like an oxygen, the idea is these electrons exist in some sort of orbital. We don't usually draw the orbitals, but you can visualize it like this, and there's nothing positive over here to keep it in check, so it actually kind of balloons outwards and pushes out more. Okay, so what this means for us is I'm actually going to look for a trend here. Let's compare 3 molecules that are essentially variations of a tetrahedral geometry. Okay, so we're going to compare CH4, NH3, and H2O. So they're essentially one atom with hydrogens attached. They're all in the second row, so carbon, nitrogen, oxygen. Okay. So what we would expect for this is carbon, the Lewis structures look like this. For nitrogen, we end up with this. Kind of skipping steps here, just showing you what the Lewis structure looks like. And for water, we can draw it like this if we felt like it. Okay. But here's the thing, is that all of these, if you look at the Vesper theory table, are all variations of tetrahedrals. Okay, they all have 4 electron groups. So this is a tetrahedral. This has 4 groups and one of them is a lone pair. So 4 and 1 would be trigonal pyramidal. And this one has 1, 2, 3, 4 groups and 2 of them are lone pairs. So that would be angular or bent. I'm going to call it bent because that's what most textbooks call it. Okay. Now here's the idea though, is that all of these, if you look at the table, say 109.5, 109.5, 109.5. But because lone pairs repel more and we're increasing the number of lone pairs as we go from left to right here, there's going to be some sort of effect on the bond angles. So I'm going to try to draw all of these with the wedges and dashes, the 3-dimensional tetrahedral look. And what we end up with is something that looks like this. They're all hydrogens. Okay. And I'm actually gonna, all the bond angles are equivalent. I'm gonna pick these 2 because it's the least cluttered, well, it's gonna clutter up the rest of the picture the least. So the bond angle is 109.5. Okay. If we draw the same thing with nitrogen, we'll replace the top one with a lone pair, and I'm gonna actually kind of draw the orbital, like there's some sort of electron density around it, and the rest of this is going to look pretty much the same. The idea, though, is that this lone pair repels more. It pushes everything else away from it. Okay? So the result is that this bond angle actually drops to 107. Okay, it dropped by about 2.5 degrees. Not a huge change, and so this thing, the ideal version says 109.5, and it's close, but it's not exactly 109.5. If you do the same thing for water, I'm going to only use I'm going to use these two, and then the other two are going to be lone pairs. What we see is that these both push on the bonds, but they also push on each other. So the lone pairs are repelling everything just a little bit more, okay? And so for this one, the bond angle drops a little bit more, and it drops down to 104.5. So you'll notice that in the grand scheme of things, this is not a huge difference. But it does point out that these bond angles on this sheet are the idealized answer. In the real world, if all the groups aren't the same, you're not going to get that number, okay? And the idea is that these things are going to get compressed by the presence of anything better than a single bond. So if you have double bonds and triple bonds and lone pairs, it's going to change these angles. I do not need you to memorize these numbers. We're just looking at trends here. Okay, let's try another example. Okay. So COBr2. Okay, if we drew this, it would, I'm just kind of skipping all the Lewis structure steps, sorry. I'm assuming that you've seen the previous chapters videos and kind of know how to draw a Lewis structure. Okay, we would get this. And if we looked at the geometry, we have 1, 2, 3 groups attached to that carbon, and none of them are lone pairs, so we expect trigonal planar, and we expect 120 degrees. Okay, so if we draw this, it would probably look, it's all going to be in one plane, so there's no wedges and dashes, but it'd look about like this. And the sheet says everything should be 120 degrees. What we find is that it doesn't change much, but double bonds do repel more than single bonds. So it's actually, the double bonds are going to be pushing more than the single bonds do. So what we find is that these bond angles are 121 degrees, which is pretty close. You'll notice that double bonds don't cause a huge difference. And because both of these are being pushed down, this is now dropped down to 118. Okay, so again, this is not a huge trend, but it is, I'm just trying to point out that these bond angles on here are not going to be perfect every time. They're approximations of an idealized version of a molecule. So the question, of course, is what does this look like on a quiz or an exam? So let's say we had a molecule. I'm just going to go ahead and draw the Lewis structure. Okay, whatever this molecule is. Now, I am not going to ask you to tell me what are all the bond angles, because you could tell me the idealized ones, but what we're worried about is which ones are a little bit different. So, let's say if you had to compare this bond angle to this bond angle, I would say, like, I'd call this A and this one B. And I would say, which is bigger? So basically, which one is larger, A or B? Okay. So what you would see is that basically, if you look at the periodic, or if you look at the Vesper theory table, you'd expect both of them to be 109.5. But those lone pairs are going to squish things together. So this lone pair would actually make this one smaller. So A should be the larger of the two. Okay. If we try this again for something like, I guess I didn't leave a whole lot of other examples here. Let's say we have C versus D. Now, D is drawn as 180 degrees, but we know from this example that it's like way less than 180. So just because it's drawn in a straight line does not mean that it looks like a straight line. Okay, so we want to know what's larger, C or D. Okay, well, this one's actually easier. You can actually compare the two different options. This one is a trigonal planar, which we expect to be 120, and this one is variation of a tetrahedral, which we'd expect to be 109.5. So the C should be bigger. But we could also compare like B versus D. So B versus D, both of these are tetrahedral. This one has 2 lone pairs, so that's going to compress things more, so B should be bigger. Okay, but that's the type of logic. So you'll note that these are not drawn with the correct bond angles. They are Lewis structures, and you need to understand how the chart works and how the lone pairs and double bonds change things. I will also point out that triple bonds really don't affect much. Even though they have, 3 times as many electrons as single bonds, you really can't have anything other than linear if you have a triple bond, and you can't get bigger than 180 degrees, so that one really doesn't affect anything. Okay, thank you.